Doubly fed electric machines are electric motors or electric generators that have windings on both stationary and rotating parts, where both windings transfer significant active power between shaft and electrical system. Usually the stator winding is directly connected to the three-phase grid and the three-phase rotor winding is fed from the grid through a rotating or static frequency converter. Doubly fed machines are typically used in applications that require varying speed of the machine's shaft in a limited range around the synchronous speed, for example a plus or minus 30%, because the power rating of the frequency converter is reduced similarly. Today doubly fed drives are the most common variable speed wind turbine concept. History: the doubly fed machine has its origins in wound rotor induction motors with multiphase winding sets on the rotor and stator, respectively, with the rotor winding set connected to resistors via slip rings for starting. However, the slip power was lost in the resistors. Thus means to increase the efficiency in variable speed operation by recovering the slip power were developed. In cross-currency mare drives the rotor was connected to an AC and DC machine set that fed a DC machine connected to the shaft of the slip ring machine. Thus the slip power was returned as mechanical power and the drive could be controlled by the excitation currents of the DC machines. The drawback of the cross-currency mare drive is that the machines need to be over-dimensioned in order to cope with the extra circulating power. This drawback was corrected in the Scherbius drive where the slip power is fed back to the AC grid by motor generator sets. The rotating machinery used for the rotor supply was heavy and expensive. Improvement in this respect was the static Scherbius drive where the rotor was connected to a rectifier inverter set constructed first by mercury arc-based devices and later on with semiconductor diodes and thyristors. In the schemes using a rectifier the power flow was possible only out of the rotor because of the uncontrolled rectifier. Moreover, only subsynchronous operation as a motor was possible. Another concept using static frequency converter had a cyclic converter connected between the rotor and the AC grid. The cyclic converter can feed power in both directions and thus the machine can be run both sub and over synchronous speeds. Large cyclic converter-controlled doubly fed machines have been used to run single-phase generators feeding 16 2/3 Hz railway grid in Europe and run the turbines in pumped storage plants. Today the frequency changer used in applications up to few tens of megawatts consists of two back-to-back connected IGBT inverters. Several brushless concepts have also been developed in order to get rid of the slip rings that require maintenance. Classification: electric machines are either single-fed with one multiphase winding set that actively participates in the energy conversion process or double-fed with two active winding sets. An active winding set has at least two AC phases with independent electrical ports, which is necessary for the production of a rotating or moving magnetic field with an electromotive force that actively participates in the energy conversion process. Since both winding sets of a doubly fed electric machine actively participate in the energy conversion process, a doubly fed electric machine operates to twice synchronous speed or twice the constant torque range with a given frequency of excitation. Many confuse the singly fed slip energy recovery induction and the field-excited synchronous electric machines with two electrical ports as doubly fed but only one port or winding set actively participates in the energy conversion process and as a result, these electric machines are not designed for operation to twice synchronous speed with a given frequency of excitation. A practical doubly fed electric machine system must operate between subsynchronous and supersynchronous speed without control discontinuity. Only practical with the evolution of control technology that avoids instability and discontinuity over the subsynchronous to supersynchronous speed range, particularly at synchronous speed where induction ceases to exist. There are now three varieties of doubly fed electric machine systems. 1. The doubly fed induction electric machine, which is the conventional wound rotor doubly fed electric machine with an active winding set on the rotor and stator, respectively, and flux vector controlled rotor excitation through a multiphase slip ring assembly. 2. The brushless doubly fed induction electric machine, which is the brushless doubly fed induction electric machine with cascaded active winding sets of unlike pole pairs on the stator assembly of which one is flux vector controlled and a flux focusing rotor assembly. and 3, synchronous electric machine system, which is the only brushless doubly fed synchronous electric machine. Unlike the doubly fed electric machine topologies that always rely on a slip in speed between the rotor and stator for operation with pronounced instability potential at synchronous speed where induction ceases to exist, the synchronous electric machine system has a brushless real-time control method that eliminates reliance on slip induction, multiphase slip ring assemblies, or any derivative of rotor flux vector control to provide stable synchronous operation to twice-synchronous speed for a given frequency of excitation with active rotor and stator winding sets. The symmetrical circuit topology and operational relationships of the wound rotor doubly fed synchronous electric machine cores with active winding sets on the rotor and stator, respectively, become the classic study for all other electric machines by optimizing their symmetry with asymmetry. For instance, by replacing the symmetrical circuit topology provided by the rotor active winding set with the asymmetrical circuit topology provided by a passive permanent magnet assembly, which has no active power port and as a result, cannot actively participate in the energy conversion process. A true doubly fed electric machine must have two or more active winding sets excited with bidirectional power in order to produce a rotating or moving magnetic field for active contribution in the energy conversion process and for providing practical operation from subsynchronous to supersynchronous speed without regions of discontinuity, such as about synchronous speed where induction ceases to exist. The DFIM and BDFIM rely on speed-based asynchronism between the rotor and stator windings to induce speed-synchronized current onto the rotor winding set. However, at the low slip experienced about synchronous speed, the time-critical measurement or excitation synthesis of shallow time differential signals makes stability increasingly elusive. The BDFIM has eliminated the multiphase slip ring assembly and partially improved stability by sacrificing size, cost, and efficiency with incorporation of a second stator armature winding set. In contrast, the BDFSM as provided by the synchronous electric machine system brushlessly propagates instantaneously derived speed-synchronized multiphase excitation to the rotor winding set without discontinuity and without relying on slip induction as exhibited by synchronous electric machines, although slip induction may be experienced as in all singly fed and doubly fed induction electric machines. Features of doubly fed machines the wound rotor doubly fed synchronous electric machine is provided by the synchronous electric machine system as the only electric machine that operates with rated torque to twice synchronous speed for a given frequency of excitation and without control discontinuity at synchronous speed where slip induction ceases to exist. In high-power applications 2 or 3-pole pair machines are common. Higher speed with rated torque means that doubly fed machines have lower cost per kilowatt, higher efficiency, and higher power density. In concept, any multiphase electric machine can be converted to a wound rotor doubly fed electric motor or generator by changing the rotor assembly to a multiphase wound rotor winding set. If the rotor winding set can transfer bidirectional active or working power to the electrical system, the conversion result is a wound rotor doubly fed electric motor or generator with higher speed and power rating than the original singly fed electric machine. These advantages can be achieved without core saturation, or by electronically controlling half or less of the total motor power for full variable speed control. As dual electromagnetic electric machines, doubly fed machines need torque current and magnetic flux to produce torque. Because there are no permanent magnets in the doubly fed machine, magnetizing current is needed to produce magnetic flux. Magnetizing current and torque current are orthogonal vectors and do not add directly. Since the magnetizing current is much smaller than the torque current, it is only significant in the efficiency of the machine at very low torque. Furthermore, magnetizing current of the wound rotor doubly fed electric machine can be shared between the stator and rotor windings. If all magnetizing current is supplied by the rotor windings, the stator will only have torque current and so unity power factor. However, by optimal current sharing the total I2R loss can be minimized. At synchronous speed the rotor current is to be DC, as in ordinary synchronous machines. If the shaft speed is above or below synchronous speed, the rotor current must be AC at the slip frequency. Thus the rotor winding requires reactive power when it is used to magnetize the machine in non-synchronous operation. Torque production requires that rotor current also has a torque-producing component in addition to magnetization. Thus active power is present in the rotor in addition to reactive power. The frequency and the magnitude of the rotor voltage is proportional to the difference between the speed of the machine and the synchronous speed. At standstill, the frequency will be the same as the frequency in the stator. The voltage magnitude is determined by the ratio of the stator and rotor winding turns. Thus if the number of turns is equal, the rotor has the same voltage as the stator. The doubly fed machine is a transformer at standstill. The transformer-like characteristics are also present when it is rotating, manifesting itself especially during transients in the grid. Due to the voltage and current behavior described above, the rotor will either require, or generate, active power depending on the speed and torque. If the machine is producing torque and operating as a motor, the rotor will generate power if the speed is below synchronous speed. At standstill, all active power fed in the stator is returned via the rotor. If the motor has rated torque, rated active power is circulating through the stator, rotor and frequency converter, and only losses are taken from the grid. The mechanical power being the angular speed multiplied by the torque of the motor is zero at standstill. Thus, like all electric machines, the efficiency of the machine is not very good at low speeds because losses depend on the current that is required to produce torque, but little or no mechanical power is produced. If the machine is operating as a motor at speeds over the synchronous speed, the mechanical power is fed in both through the stator and rotor. As a consequence, the efficiency is now better than with singly fed motors. For example, the doubly fed electric machine with equal stator and rotor turns produces same torque at double speed as a singly fed electric machine. The losses, being roughly proportional to the torque, are quite the same. Thus efficiency, which is the power taken divided by the total power produced, is better than singly fed electric machines. Naturally, one has to take into account the loss of the power electronic control equipment. However, the frequency converter of the doubly fed machine has to control only 50% or less of the power of the machine, and thus has about half of the loss of the singly fed machine's frequency converter that has to pass through 100% of the power. Since efficiency is the ratio between the output power to the input power, the magnetic core efficiency of a wound rotor doubly fed machine, which has just two winding sets of loss but shows twice the power for a given frequency and voltage of operation, is comparable to the magnetic core efficiency of permanent magnet machines with just one winding but without magnetizing current. Coupled with the low-power electronic controller, the wound rotor doubly fed electric machine system would be more efficient than permanent magnet machine systems without magnetizing current. For operation as a generator, a similar situation exists. At subsynchronous speeds, the stator is generating the power, but part of it has to be fed back to rotor. At supersynchronous speeds, both the rotor and stator are producing power to the grid. Thus the current rating of the rotor converter is defined by the maximum active current required by the torque production and the maximum reactive current required to magnetize the machine. Doubly fed electric machines outperform the others in supersynchronous speeds. They can operate at constant torque to twice synchronous speed if each active winding is rated at half the total power of the machine, and can provide continuous operation between subsynchronous through supersynchronous speed range. Doubly fed machines do not produce more continuous rated torque per volume than singly fed machines. The bigger power rating is due to the higher speed attainable without weakening the magnetic flux. The short-time maximum torque of a wound rotor doubly fed electric machine is, however, much higher than all other electric machines, including induction or permanent magnet machines, because increasing torque current does not directly increase air gap flux, which leads to core saturation. In practice, torque current increase is only limited by the temperature of the windings and the maximum current capability of the rotor frequency converter. With one of the two armature winding sets residing on the rotor and stator body, respectively, the rotor real estate of the wound rotor doubly fed machine actively participates in the energy conversion process, which is different from all other electric machines, including permanent magnet synchronous machines. As a result, the magnetic core of the wound rotor doubly fed electric machine shows highest power density. Changing of the direction of the rotation requires the swap of two stator phases near zero speed if symmetrical speed range in both directions is required. It is common to dimension the doubly fed machine to operate only at a narrow speed range around synchronous speed and thus further decrease the power rating of the frequency converter in the rotor circuit. Typical applications of doubly fed machines have been high power pumps and fans, hydro and wind generators, shaft generators for ships etc. Where operating speed range has been quite narrow, less than a plus or minus 30% of the synchronous speed and only small power is required in the subsynchronous range. Due to the high rotor to stator winding turns ratio that is typical in these applications and the high voltage thus induced in the rotor at standstill, the starting of this kind of restricted operating speed range motor drive is usually done with rotor resistors in induction motor mode. When speed is in the operating speed range, the resistors are disconnected and the frequency converter is connected to the rotor. If the starting torque is low enough, it is also possible to short-circuit the stator and use the frequency converter and the induction motor control mode to accelerate the motor to the operating speed range. Generators, naturally, don't usually need any additional starting means because wind or water is used to accelerate the machine to the operating speed range. Electronic control equals, the controller, a frequency converter, conditions bidirectional, speed synchronized, and multiphase electrical power to at least one of the winding sets. Due to the lack of damper windings used in synchronous machines, the wound rotor doubly fed electric machines are susceptible to instability without stabilizing control because torque is a function of position. Pioneering work of Drs. Albertson, Long, Novotny, and Schmitz from the engineering department of the University of Wisconsin realized this must be overcome with instantaneous control. Like any synchronous machine, losing synchronism will result in alternating torque pulsation and other related consequences. Doubly fed electric machines require electronic control for practical operation and should be considered an electric machine system or more appropriately, a variable frequency drive. Wound rotor doubly fed electric machine. Construction equals, two multiphase winding sets with similar pole pairs are placed on the rotor and stator bodies, respectively. Since the rotor winding set actively participates in the energy conversion process with the stator winding set, utilization of the magnetic core real estate is optimized in contrast to all other electric machine types. The doubly fed machine operation at unity stator power factor requires higher flux in the air gap of the machine than when the machine is used as wound rotor induction machine. It is quite common that wound rotor machines not designed to doubly fed operation saturate heavily if doubly fed operation at rated stator voltage is attempted. Thus a special design for doubly fed operation is necessary. A multiphase slip ring assembly is traditionally used to transfer power to the rotating winding set and to allow independent control of the rotor winding set. The slip ring assembly requires maintenance and compromises system reliability, cost and efficiency. Attempts to avoid the slip ring assembly are constantly being researched with limited success. Control equals, although the multiphase slip ring assembly reduces reliability and requires regular maintenance, it allows easy control of the rotor winding sets so both multiphase winding sets actively participate in the energy conversion process with the electronic controller controlling half of the power capacity of the electric machine for full control of the machine. This is especially important when operating at synchronous speed, because then the rotor current will be DC current. Without slip rings, the production of DC current in the rotor winding is only possible when the frequency converter is at least partly located in the rotor and rotating with it. This kind of rotor converter naturally requires its own winding system for power transfer out of or into the rotor. Furthermore, there are thermal and mechanical constraints of the power electronic assembly in the rotor. However, high-speed alternators have had electronics incorporated on the rotor for many years. Furthermore, high-frequency wireless power transfer is used in many applications because of improvements in efficiency and cost over low-frequency alternatives. Efficiency equals, neglecting the slip ring assembly. The theoretical electrical loss of the wound rotor doubly fed machine core in supersynchronous operation is comparable to the most efficient electric machine systems available under similar operating metrics. The efficiency is similar because the total current is split between the rotor and stator winding sets, while the electrical loss is proportional to the square of the current flowing through the winding set. Further, considering that the electronic controller handles less than 50% of the power of the machine, the wound rotor doubly fed machine theoretically shows nearly half the electrical loss of other machines of similar rating. Power density neglecting the slip ring assembly and considering similar air gap flux density, a physical size of the magnetic core of the wound rotor doubly fed electric machine is smaller than other electric machines because the two active winding sets are individually placed on the rotor and stator bodies, respectively, with virtually no real estate penalty. In all other electric machines, the rotor assembly is passive real estate that does not actively contribute to power production. The potential of higher speed for a given frequency of excitation, alone, is an indication of higher power density potential. The continuous constant torque speed range is up to 7,200 rpm at 60 Hz with 2 poles compared to 3,600 rpm at 60 Hz with 2 poles for other electric machines. In theory, the core volume is nearly half the physical size compared to other machines of similar rating. Cost neglecting the slip ring assembly, the theoretical system cost is nearly 50% less compared to other machines of similar rating because the power rating of the electronic controller, which is the significant cost of any electric machine system, is 50% than other electric motor or generator systems of similar rating. Peak torque with the symmetrical or dual-ported transformer topology of two active winding sets on the rotor and stator, respectively, the wound rotor doubly fed electric machine core produces nearly twice the peak torque of any electric machine by similarly increasing torque current without affecting air gap flux density or saturating the magnetic core because the torque currents on each side of the air gap are neutralized. For all electric machines, peak torque current increases dissipation while reducing efficiency. Double-fed induction generator, DFIG for double-fed induction generator, a generating principle widely used in wind turbines. It is based on an induction generator with a multiphase wound rotor and a multiphase slip ring assembly with brushes for access to the rotor windings. It is possible to avoid the multiphase slip ring assembly, but there are problems with efficiency, cost and size. A better alternative is a brushless wound rotor doubly fed electric machine. The principle of the DFIG is that rotor windings are connected to the grid via slip rings and back-to-back voltage source converter that controls both the rotor and the grid currents. Thus rotor frequency can freely differ from the grid frequency. By using the converter to control the rotor currents, it is possible to adjust the active and reactive power fed to the grid from the stator independently of the generator's turning speed. The control principle used is either the two-axis current vector control or direct torque control. DTC has turned out to have better stability than current vector control, especially when high reactive currents are required from the generator. The doubly fed generator rotors are typically wound with 2 to 3 times the number of turns of the stator. This means that the rotor voltages will be higher and currents respectively lower. Thus in the typical a plus or minus 30% operational speed range around the synchronous speed, the rated current of the converter is accordingly lower, which leads to a lower cost of the converter. The drawback is that controlled operation outside the operational speed range is impossible because of the higher than rated rotor voltage. Further, the voltage transients due to the grid disturbances will also be magnified. In order to prevent high rotor voltages, and high currents resulting from these voltages, from destroying the IGBTs and diodes of the converter, a protection circuit is used. The crowbar will short-circuit the rotor windings through a small resistance when excessive currents or voltages are detected. In order to be able to continue the operation as quickly as possible, an active crowbar has to be used. The active crowbar can remove the rotor short in a controlled way, and thus the rotor side converter can be started only after 20 to 60 milliseconds from the start of the grid disturbance when the remaining voltage stays above 15% of the nominal voltage. Thus it is possible to generate reactive current to the grid during the rest of the voltage dip and in this way help the grid to recover from the fault. For zero voltage ride-through it is common to wait until the dip ends because with zero voltage it is not possible to know the phase angle where the reactive current should be injected. As a summary, a doubly fed induction machine is a wound rotor doubly fed electric machine and has several advantages over a conventional induction machine in wind power applications. First, as the rotor circuit is controlled by a power electronics converter, the induction generator is able to both import and export reactive power. This has important consequences for power system stability and allows the machine to support the grid during severe voltage disturbances. Second, the control of the rotor voltages and currents enables the induction machine to remain synchronized with the grid while the wind turbine speed varies. A variable speed wind turbine utilizes the available wind resource more efficiently than a fixed speed wind turbine, especially during light wind conditions. Third, the cost of the converter is low when compared with other variable speed solutions because only a fraction of the mechanical power, typically 25 to 30%, is fed to the grid through the converter, the rest being fed to grid directly from the stator. The efficiency of the DFIG is very good for the same reason. Brushless doubly fed versions Brushless doubly fed induction electric machine Brushless doubly fed induction electric machine is constructed by adjacently placing two multiphase winding sets with unlike pole pairs on the stator body. With unlike pole pairs between the two winding sets, low-frequency magnetic induction is assured over the speed range. One of the stator winding sets is connected to the grid and the other winding set is supplied from a frequency converter. The shaft speed is adjusted by varying the frequency of the control winding. As a doubly fed electric machine, the rating of the frequency converter need only be fraction of the machine rating. The brushless doubly fed electric machine does not utilize core real estate efficiently and the dual winding set stator assembly is physically larger than other electric machines of comparable power rating. In addition, a specially designed rotor assembly tries to focus most of the mutual magnetic field to follow an indirect path across the air gap and through the rotor assembly for inductive coupling between the two adjacent winding sets. As a result, the adjacent winding sets are excited independently and actively participate in the electromechanical energy conversion process, which is a criterion of doubly fed electric machines. The type of rotor assembly determines if the machine is a reluctance or induction doubly fed electric machine. The constant torque speed range is always less than 1800 rpm at 60 Hz because the effective pole count is the average of the unlike pole pairs of the two active winding sets. Brushless doubly fed electric machines incorporate a poor electromagnetic design that compromises physical size, cost, and electrical efficiency, to chiefly avoid a multiphase slip ring assembly. Brushless wound rotor doubly fed electric machine The brushless wound rotor, synchronous doubly fed electric machine incorporates the electromagnetic structure of the wound rotor induction doubly fed electric machine but replaces the traditional multiphase slip ring assembly with a brushless real-time emulation control means that independently powers the rotor multiphase winding set with speed and phase synchronized AC excitation automatically and without delay is hypothesized by electric machine experts since the 1960s to avoid torque angle instability and slip induction discontinuity. Without experiencing control discontinuity between subsynchronous and supersynchronous speeds while under stable instantaneously controlled excitation, the rotor multiphase winding set of only the BWRSDF becomes an equal power contributing participant in the electrical to mechanical power conversion process in conjunction with the stator multiphase winding set and as a result, the rotor winding set provides the second armature for a dual armature electric machine system. In accordance with synchronous operating principles, the rotor armature cannot rely on induction principles as a result of a slip between the speeds of rotor and stator winding sets because slip induction ceases to exist about either side of synchronous speed, which always leads to discontinuous operation. Without the reliance on slip induction for practical operation, the brushless wound rotor synchronous doubly fed electric machine operationally differs significantly from wound rotor doubly fed induction electric generators or motors, which traditionally include a multiphase slip ring assembly, and the so-called brushless doubly fed induction or reluctance electric machines that rely on very different principles of unlike pole pair slip induction for operation. The doubly fed induction electric machines have been relegated to high-power generator applications, such as wind turbines, where their higher efficiency and lower cost as a result of doubly fed prevail over instability, which is externally mitigated by the inertia of the prime mover. Considering the speed of all electric machines is determined by the number of pole pairs and the frequency of excitation, electric machines with a two-pole armature operate at 3600 rpms under 60 Hz of excitation, but only a true BWRS-DF can achieve stable and contiguous operation to the supersynchronous speed of 7200 rpms with the same torque performance, which is tantamount to twice the power density of all other electric machines, including permanent magnet and reluctance electric machines, by reasonably assuming the rotor and stator armature assemblies are equally power-rated and occupy virtually the same physical volume as was qualified by at least pioneering electric machine experts from the 1960s, such as Professors D.W. Novotny, Norbert L. Schmitz, and Willis F. Long from the Electrical Engineering Department of the University of Wisconsin. Since efficiency and cost are normalized to power rating, other ramifications are half the cost and half the electrical loss, and the electronic controller need only control the power of one armature of the electric machine. Operationally comparable to a dual-ported transformer, the air gap flux remains virtually constant regardless of the level of flux producing torque current, and as a result, the brushless wound rotor, synchronous doubly fed electric machine can achieve multiply higher peak torque density than all other electric machines without saturating the magnetic core, which is an attractive attribute for transmission-less electric propulsion systems, such as electric vehicles. In addition, this same attribute allows the air gap flux density of only the BWRS-DF to be designed closer to the saturation limit of the magnetic steel core without operational concern and effectively allowing a higher air gap flux density than other electric machines. Like any synchronous electric machine with excess VAR capacity in conjunction with field control and torque angle control, the BWRS-DF can be a synchronous condenser with the ability to balance the electrical AC system, such as the smart grid, with leading to lagging or unity power factor adjustment. Without practical invention, pioneering experts have only theorized that stable excitation control of the rotor armature for a true BWRS-DF must be a real-time emulation control method that without delay, automatically and senselessly compensates for the destabilizing torque angle effects from at least external shaft perturbations further complicated by the effects of slip induction. Very different from RTEC, today's state-of-art field-oriented control rely on the imprecision and costly time delays of simulation control methods that sequentially measure speed and position, then estimate the rotor time constant, and finally, synthesize the excitation frequency and waveform, all by an offline digital electronic processor, which further aggravate the instability and slip induction issues as a result of control delays and imprecisions that have prevented the realization of a true BWRS-DF electric machine in the past. For brushless operation, rotor multiphase power cannot propagate through the traditional multiphase slip ring assembly with its issues of additional cost, efficiency, size, maintenance, suitability, and reliability. Without including the multiphase slip ring assembly or a TEC, the basic symmetrical topology and relationships of the BWRS-DF are the classic introductory textbook study of electric machines, and by simply optimizing their high performance with asymmetry, the relationships of the BWRS-DF become the study for all other electric machines, including permanent magnet, induction, and reluctance electric machines. So although the attractive performance attributes of the BWRS-DF have been studied and understood for decades, the formidable invention of a practical brushless RTEC has not been forthcoming, and as a result, the BWRS-DF has been kept from practical application until recently. See also, electrical motor, electrical generator, singly fed electric machine. References. External links, Dufour, Christian. Bar copyright Langer, Jean. Real-time simulation of doubly fed induction generator for wind turbine applications. Roberts, Paul C. Study of brushless doubly fed machines. Contributions in Machine Analysis, Design and Control. Emmanuel College, University of Cambridge.